Yeah, thank you so much. Thank you everyone for joining. I know the last session of the conference, it's a long haul, so appreciate you coming today, and again, everyone for joining remotely. Excited to talk here about unsupervised learning for detecting data quality issues and doing that in a scalable way. I'll take you through a little bit of my background, and then I'll introduce this problem and show you what it looks like in an example. And then I'll actually take you through the algorithm, how it works behind the scenes, and we can talk about some of the challenges at the end in testing it and ensuring that it works effectively. So how did I get here? I actually started my career 20 years ago in financial services at Ernst & Young, doing at the time what was called predictive modeling. And one of my favorite projects I worked on was to predict which physicians would get sued for medical malpractice. Which is pretty fascinating. There's a lot of different things you wouldn't necessarily think go into that. And early on, learned a lot about third-party data sources and kind of complex data, encountered a lot of data quality issues. I then went into advertising technology, as one was wont to do back in the late 2000s, early 2010. Went to Sailthrough, did a lot of personalization there, recommendations of content for advertisers and for publishers. And then came out to California to work at Instacart. I ran data science and machine learning at Instacart, really a lot of fascinating problems there. Optimizing grocery delivery, ensuring grocery items are in stock when people order them, the personalization of the grocery experience online. So a lot of interesting challenges, and a company that was very data-driven. You just can't do that business model without using data. And so machine learning was integrated into everything that we did. And data quality was a constant challenge there as well. I left about 4 years ago, took 6 months off, and then joined my co-founder, Elliot, who ran product and growth at Instacart, to start Anomalo, focused on data quality and trying to create a more scalable approach to monitoring data quality in cloud data warehouses like Databricks. So you've all seen many different versions of this modern data stack slide. This is a really simplified version of it. Organizations today are ingesting a tremendous amount of data. Basically, every scrap of data that can pass through the organization can be captured. It could be event data, it could be data from databases, production database, SaaS applications, data feeds. It's easy to get that data into a data warehouse like Databricks, easy to transform and orchestrate that data, increasingly using tools like dbt, using orchestration tools like Airflow. And then you can create BI and analytics layers on top of that to democratize decision-making with data throughout the organization. And you can build ML and data science platforms in order to really optimize the product experiences themselves. This is all wonderful. If you go back 20 years, it would have taken you many hundreds of engineers to build something like this. And now it can be done relatively simply by 1 or 2 people. But data quality is a huge issue in this environment. You can have a wide variety of different data quality issues. You can have missing events. You can have JSON schemas that change. Data can arrive late. You can have duplicate data. Just at least once processing generates a lot of unknown duplicates out there. You can have APIs that change. You can have third-party data feeds that just are missing. And then the transformation layer itself can introduce a lot of issues. There can be bugs in the SQL. You can have jobs that fail. The net result of all of this is that data in that data warehouse can be delayed, it can be incomplete, it can be invalid, or it can just be messed up. It can just be anomalous. For the decision makers using your BI and analytics platform, you can have broken dashboards, right? Where users come to the dashboards and it's just not working at all. And that's a terrible experience, and they'll stop coming if they get that enough. Or possibly even worse, the dashboard can be working, but the metrics themselves can be misleading. And that can lead to fire drills or to really bad decisions. On the ML and data science side, the models themselves can be very unstable. And then when you're making predictions, if there's a sudden change in features, that can lead to wildly erratic predictions, and that can completely change the user experience, often for the worse. So we created Anomalo to be a platform that can sit next to data warehouses like Databricks and to be able to monitor that data and identify issues and notify people in the organization that care about those issues before the downstream users notice them. So how do you do that? How do you do data quality monitoring? How do you do it at scale? Broadly, we see 3 different approaches to solving this problem. Our platform actually does all 3. I'll walk you through each one. We're going to spend most of our time on the unsupervised, but I'll spend a little bit of time on how each one works and how they work together. So the first approach is what we call validation rules. These are hard and fast constraints that subject matter experts are placing on the data. Things like this column should be 100% unique, or this relationship should hold true for every row. These are pretty simple to set up as an individual test, right? You do need to do a lot of work. You need to say exactly what test I want, what are the constraints, what data is it going to be applied to. The real challenge with these comes with scalability. If you've got hundreds or thousands of tables, each with hundreds of columns, each with hundreds of meaningful segments of data, who's going to go in and write all of those rules? And if you auto-generate those rules, who's going to ensure that they're relevant and that you don't get lots of false positives? Typically, what we see happening here is as you create these rules, people don't maintain them. And they end up sending bad notifications, and people get burned out, they get alert fatigue, and the initiative fails. At Instacart, when I left, we had a system that did this. We had 1,000 rules in production. The other challenge is we were always getting some new issue that we hadn't written a rule for. We had only protected ourselves against the things we already understood. So another approach to data quality monitoring is just let's define lots of metrics. And so a metric could be a key performance indicator for your business, or it could be a data quality statistic. Here we're computing the percentage of time a specific column is null. And you can see there's a time series model fit around that. That time series model is taking into account things like changes in trend, day of week seasonality. And on this very most recent day, there's a big spike in the null value percentage. And so if that happened in a data set you cared about for a column that you cared about, you might want to get notified about that. And so that can be a powerful approach. But again, there's huge scalability issues. Back to the situation where you've got hundreds of thousands of tables, hundreds of columns, who's going to write all of the metrics that matter? And if you did write all of those metrics and anything happened, you would get tons of notifications. And how many of those notifications would really be meaningful? So in the end, we see these as being great for KPIs, things you really care about, but you can't do this at scale. And so the final approach is to use what we call unsupervised monitoring. And that's what I'll take you through in the rest of the talk. This is where we use machine learning to automatically detect material adverse changes happening in the data itself. We are sampling records from the table as a whole and using machine learning to identify, are there increases in null values? Are there distribution changes that matter? Are there segments of data that have disappeared or dropped in row count significantly? Or even are there columns whose relationship has changed with one another? And the really powerful thing about this approach is all you have to do to configure it is point it at a table and say, I want to start monitoring it. And the algorithm begins running. It learns online. The algorithm is retrained every single day, constantly adapting to what's happening in the table. And if something seriously wrong happens, it will send you a notification about it. Now, of course, there's no free lunch. This isn't a perfect solution. You can't just rely upon this monitoring approach, and it's for a few reasons. First, if you compare it to metric anomalies, when you say I want to monitor a metric, you're actually putting a tremendous amount of weight on specific subset of the data. You're saying the specific columns, the specific rows that matter for that metric, those are what's really important to me, and I want to pay a lot of attention to it. Versus the unsupervised monitoring, it's going to treat every row, every column as being equally important. So it doesn't have that level of focus. Similarly, if you compare it to the validation rules, when you set up a validation rule, you as a user or your subject matter expert is bringing their expertise about what they think the data should look like. It could have always been broken, right? And because of that, their expertise might be able to identify that by expressing it as a rule. When we do unsupervised monitoring, it's looking for sudden changes. So it's looking for the regressions that are happening in the data, helping you find those and fix them along the way. It's not going to tell you if the data was always wrong. OK, so let's talk through an actual example. Let's pick a piece of data. I'll show you what it looks like in Anomalo to actually run unsupervised learning. We'll break the data. We'll introduce some chaos. You can see the kinds of visualizations that come out. Then I'll step back and we'll go through the algorithm itself. So the data set that I'm going to use is a pretty simple data set. It's a bunch of ticket sales data. And I've got just a sample of the table here. If we zoom into that row on the bottom, this is a performance by the Who. It's at Reliance Stadium in Houston, Texas. There were 4 tickets listing for sale at $131 per ticket. So this is a typical example of the kinds of transactional or event-level data that you might want to monitor. So in Anomalo, to set this up, the first thing that you would do is you would go in and search for this table. And so you can just drop that into the search box. It would limit it to just the tables that match that string, and then you just click on the configure button. As soon as you've configured the table, it brings you into this table homepage, and it just asks you one question up front. What time column do you want to use? The time column is important because we want to be able to query for the most recent data in the table. And we automatically recommend what time column to use. You would just click on that, and you would have this configured. The first thing that then happens is we can profile the data. So draw a random sample of records from the most recent date. Here you can see on the left-hand side all of the columns, and then you can see the types of the columns, and then a visualization that just shows you the most common values in each column. And so, for example, if you take a look towards the bottom, venue city, New York City is the most common venue. Below that, New York is the most common state. This is interactive, so when you're actually using the application, you can hover over, you can sort in different ways, and get a quick head kind of wrapped around what's actually happening in this table. And then the actual monitoring is above that profiling, and this is the table homepage where most of the work happens in Anomalo. And you can see there are these 6 different sections, each with a green check. The first 4 sections at the top all run in a totally automated way. The bottom 2 are the key metrics and the validation rules. What I was talking about earlier, you can come in and add a metric and monitor that for changes, or add a validation rule to say this data should be perfect in some specific way. But the 4 up top are fully automated, and it begins with data freshness. Are new records arriving in this table? Has the table been updated? And then goes to data volume automatically. Data volume looks at the row counts themselves and makes sure that you're not missing a big chunk of records. It's pretty common to have, for some reason, data's delayed and the last hour hasn't completed, or a specific segment of the data hasn't completed. And so this data volume really gates the rest of the checks to make sure you don't run a bunch of these checks on data that's only halfway there. Below that are missing data and table anomalies. And inside of the table anomalies is our full unsupervised machine learning algorithm, what I'll show you here. But we also have algorithms that are looking explicitly for duplicate data, looking for columns being dropped, looking for variants of missing data, and profiling those with more precision, often using the machine learning underneath the hood. OK, so that's what the setup looks like. We've got the table. It's configured. We're monitoring it. Now, let's mess with the data. Let's introduce a synthetic issue. So one of the fun things that we built at Anomalo and continue to evolve is our chaos library. And so you can drop into a command line client in Anomalo, and you can find a whole library of chaos operations. These are just the first few. And they are all replicating different types of anomalies that we typically see, data quality issues that we typically see in data. We use this to demo, so we can call any of these and introduce synthetic issues and show you what it looks like. But we also use it in our unit tests. So to ensure that the application is working correctly, we've got this library to be able to inject synthetic issues into Databricks or BigQuery or Snowflake, right? It can work across all the platforms. And then we also use it to test our machine learning. And so at the end, I'll show you what that looks like. We actually randomly inject chaos using this library. In this case, we're just going to do one operation so we can see what happens. And so the specific operation we're going to do is what we call time column value. So at a specific point in time, for a specific column, we're going to introduce a bad value. We have to tell it, what table do we want this to apply to? It's the fact listing table that we've set up monitoring on. Then we need to tell it what column do we want to mess with. So we're going to do the number of tickets column. What value do we want to inject? I go ahead and pick 40. I happen to know that's particularly high and unusual. We need to tell it what time column to use. So we're going to use the list time column that we use to configure the table in order to make sure that it only happens on a specific date. When I was creating these slides, it was May 3rd. And so that's why this says May 3rd. We're going to do that chaos for 30% of the data. So it's not going to be all of the records. It's just going to be 30%. And we're going to make it a little bit trickier. We're going to take a specific geography and only apply the chaos in New York. So the venue state field has to be equal to New York for this to happen. We can then go back into the application, and we can take the no anomalous records check, which is the full unsupervised learning, and rerun it manually. And when we do that, you can then click into the check and actually watch it do its execution. It has an execution log. And you can see the beginning of that execution log here. We're connecting to the data warehouse, and then we're querying for a sample of records from each day. This is just a test environment, so a relatively small sample of records that we're querying for. And you'd actually see the sampling query there. That's one of the nice things. You can see the debugging of the sampling query. It's a little bit complex because we're pulling it from multiple days. And then as soon as that query comes back, we've pulled that data into memory on the Anomalo application, and we're running the machine learning, identifying material issues, generating visualizations, sending a notification to Microsoft Teams or Slack or email, as specified by the user. And so all of the work is happening there behind the scenes. If we come back to the table homepage, that check is now failing. There are also a few key metrics and validation rules that I had set up that were also failing. And so one of the really neat things about this is keep in mind for the unsupervised learning, we didn't tell it anything about the table. All we did is, I want to monitor this data. We didn't tell it what to look for, and it's able to find it entirely on its own. And so what does it actually look like? When you click in and see the visualizations, how do we explain this? Well, it begins with a summary. And you can see the summary at the top in natural language that it's identified that it's the column number of tickets. So it knows that's the column that's messed up. And it's able to pick out that it's the value 40 in particular that's increased. Right? We've got a bunch of new records for the value 40. But it's also able to characterize how strong is this anomaly. In this case, it's pretty meaningful. This is a very different value appearing in a significant chunk of the distribution of the records. And so it's an unusual change. And one of the neat things is that we are maintaining state over time. And so every day that this runs, we're able to keep track of, well, how severe was the anomaly? And then we do time series modeling on that in order to learn a threshold. And so that's the learned threshold here. And so given the natural amount of chaos and kind of background noise happening in this table, this is a particularly unusual change and one that you might want to be notified about. OK, so that's a good top-level summary of what's happening. Let's go a little bit deeper. Underneath that, you can actually see a profile of the distribution of the column. And here we do this tornado visualization. And the algorithm automatically selects what kind of statistic to summarize here. In this case, it's doing the top values, because just one value in particular has changed. In other cases, it might bin the data. And you can see the distribution of the values on the second, the day before we introduced the issue, versus the distribution on the third. And if you were to hover over this 10.4%, we would summarize it for you. And that's all of the records that have been messed up, right? That 40 value wasn't there at all the day before, and now all of a sudden it's 10.4% of the records. Now, you might be asking the question, well, where is this happening? And why is this happening? And so the next thing underneath that would be an actual sample of bad and good records. And you can grab these blue bars and scrub through it and be able to see a bunch of these records. And you can see the record on the left has a value of 40 for number of tickets, and that's been highlighted. The one on the right has a normal value for number of tickets. It's 8. And really the challenge here is to squint and look at these and try to answer the question, where is this happening? What segment of the data is this happening in? As a user, that's what you would start to do. You would try to figure out, well, how is this happening? What geography? What was it time of day? Is it a specific seller? We actually go ahead and then do that analysis for you. And this is called a root cause analysis. We'll go through those samples. We'll identify every segment. And then we'll do statistical analysis to determine how prevalent is that segment in the bad data versus how prevalent is it in the good data. We'll cluster the segments together so that you don't end up with 15 different variants of the segment New York. If you've got a bunch of columns that are all related, they'll all be clustered together. And then we'll rank at the top the ones that are most statistically significant in terms of indicating exactly where is this issue happening. And so here, if you hover over, you get this tooltip, which shows that the segment venue state New York, it's 100% of the bad rows, but it's only 30% of the good records. And that's by far the most significant explanation here. And if you go back to the chaos that we did a few slides ago, remember I put in a where SQL clause that said the venue state should be New York. And so the algorithm's able to recover not just what column was affected, what was the nature of the change, how do you summarize the change, but also where in the data did the change happen. And so often when you're applying this monitoring to fact tables, you bring a lot of context about that data. And so we can use that context to really speed up the root cause analysis. OK, so that's an example of what's actually happening. Now let's go behind the scenes and talk through how the algorithm works. So suppose we had two samples of data, a sample of this table from today and a sample of the data from yesterday. In that simple case, imagine building a machine learning model that's going to take each one of these rows and try to predict on which day did that row come from. Did it come from yesterday or did it come from today? If you can build that machine learning model, then something in that machine learning model learns something about the data, right? If it's able to predict with some confidence on which day did each record come, then something must have changed. So that's actually the kind of core insight here. And I'll walk you through what does that actually look like. So again, we want to predict which day did each record come from. And so the first step is to just create a response variable. It's just, pretty straightforward. Let's call today's data all 1, call yesterday's data all 0. Then we can take this data and encode all of it into features, into a feature space. And in this case, the features encodings, it can be a wide variety of things, but they need to handle all of the common types of data. And so they need to handle timestamps and dates. They need to handle strings. They need to handle integers and floats. They may also need to handle things like arrays or dicts or more complex JSON columns, being able to expand into those to be able to generate all of the features that you might want. And so one of the things that we've done in Anomalo is to have a feature generation process that's entirely automated. So for any table, any sample of data, we're able to identify what are candidate features we should include and automatically generate those features. OK, so now we have features and a response. Then we just need to build a machine learning model to predict, can we learn anything about that response outcome? And so we use gradient boosted decision trees, very powerful for this kind of tabular structured data. We're using relatively small samples of data. It could go up to, say, 100,000 records. And so you do need something that can be relatively fast. But you're not going to get a lot of value by building a deep learning model here. There's not enough data, and it needs to generalize across any kind of tabular data that we might encounter for any customer. Plus, we're going to retrain this model every single day. So it does need to be pretty quick. And you can simply evaluate that model. Was it able to materially separate the data or not, right? If you look at the number of steps on the x-axis, how many decision trees we're adding in the gradient boosted decision tree, if that flatlines, right, if we're never able to really learn anything, especially on the validation set, then these two samples of data are essentially identical as far as the machine learning algorithm can tell. OK, that's great. So now we can tell at a high level are the data sets different, but it's not enough. The next step we need to do is understand what aspects of the data allowed the machine learning model to be able to differentiate yesterday's data from today. And so we use SHAP values for that. It's a pretty magical library and approach to being able to do game theoretic fair credit down to individual values in the table for how that value helped the algorithm make the decision. It essentially approximates this machine learning algorithm with a local linear estimation of what the algorithm is doing. And using that, you can then credit it. And you can say, well, the price per ticket was a big part of what made this particular record be likely to come from today versus yesterday. And so we take that algorithm, and you can essentially roll it up across the features and get a sense of the heat that the algorithm has in terms of being able to separate yesterday versus today for every single value in the table. And that's kind of super cool, right? Now we've actually taken this two samples of data, and we've got a credit score for every value for whether or not it indicates that value makes that record likely to come from today or yesterday. Honestly, that then is just the basis for all of the visualizations, right? With that crediting, we can now answer the question, well, how significant is the difference between the data yesterday versus today? We can aggregate it across every column and identify what columns have the largest anomaly score values. we can take the column that has 90% of the anomaly score values, and we can profile that and identify, well, what values and what encoder helped us separate that data. And then we can split the records that are very different from the records that are very consistent across time and do the root cause analysis on that to figure out where in the table did this anomaly occur. So that really does power a lot of the visualization and insights that we're able to generate off of this approach. OK, all well and good, but that was a really simple example, right? Just comparing one day to the prior day and ignoring a lot of complicated things that happen when you're working with a bunch of real data. So let's talk through a few of those challenges. The first obvious one is seasonality, right? What if this data is changing by day of week, if it's changing by day of month, by season of year, by holidays? And so we actually end up building models where we're not just comparing today to yesterday, we'll compare it to multiple prior lookbacks. We'll compare it to the same day a week ago, same day last month, et cetera. That's at the core machine learning algorithm level. We also generate a lot of metadata statistics about the algorithm's performance, and then use time series models on that metadata over time to be able to identify if there are features that are in some other way correlated with seasonality or have some other seasonality trend to them, and then we dampen those features down. The other thing that you run into immediately is there's lots of features that obviously separate yesterday's data from today, right? There's a date column. There's a list time column, right? Those columns are obviously going to be different today versus yesterday. And so your machine learning algorithm will immediately recognize, this data is different. It's got a different date. And if you send that notification to the user, they're going to be pretty frustrated. That's obvious, right? And so we need to be able to go in and identify what we call these time-based features, features that are kind of auto-correlated with time. A lot of IDs behave this way, too. They're always auto-incrementing, so they're always getting bigger. And so the machine learning algorithm will learn that today's data has bigger IDs, but that's not really an anomaly. So we need to find those and actually remove them entirely, or else they soak up too much of the machine learning model's attention. A lot of tables are chaotic. You might have one table that is a bunch of operational data for marketing, and it's changing dramatically on an entirely random process depending upon who's launched what marketing campaign and what geography. And that's going to have all sorts of unusual changes happening in it. Versus another table might be the event log detail for a giant social media platform. And at a global level, 40 billion events per day, it's going to be pretty consistent over time. And so we actually learn to be able to separate out how chaotic is the table. We'll learn a threshold that's dynamic, and we'll even learn how chaotic each individual column is. You need to be able to cluster across columns. Earlier we found a problem with geography. It's not uncommon to see geography represented in 10 different ways in a table, right? You might have country, region, geography, zip code, geohex, right? All sorts of different geography indicators that are all clustered together. And so, if your geography pipeline breaks and they all go null, you're going to have an anomaly in all of them. And we need to be able to cluster that together because it's actually a pretty serious event affecting multiple columns. Accuracy is definitely a concern. You want to make sure that when this sends an alert, it's a meaningful change. But you also don't want to miss something. And so being able to balance false positives and false negatives is really important. I'll talk about that a little bit on the next slide. And then finally, it needs to be able to perform. So this has to scale to billions of rows. It has to scale to thousands of columns. And really, it is rows by columns that drive the complexity of the algorithm. Scaling to billions of rows, fortunately, we're connected to a platform like Databricks. And so we do random sampling in the data warehouse itself to only extract a finite random sample. And that tends to give us an upper bound for both runtime and memory usage. So let's talk about testing. And this is really the last slide. So to test an algorithm like this, the first foundational approach we use is just a backtest. And so we'll take a data set. This is actually a bunch of complaints for 311, the number you call when you have an issue in the city from the state of New York or the city of New York City. All of the columns are along the left side, the vertical axis. And then the horizontal axis is time. And what you can do is you can take your algorithm, this unsupervised learning algorithm, and just pretend that we're meeting this data set for the first time at the beginning of this time series, and then walk through sampling the data each day, running the algorithm and identifying how severe is the anomaly and for what column is it being affected. And you can actually see the heat here is how significant the anomaly score is for every column over time. And so you kind of hover over that and see how significant are these different historical anomalies happening in the different columns. This is useful. It would give you a sense for a specific table. How likely is this to alert, and what kinds of issues is it likely to find? But it doesn't give us a North Star metric to figure out how to tune the algorithm. Right? If we want to change parameters in the gradient boosted decision tree, or we want to change the feature encoding space, or some other logic around the algorithm, this isn't going to help us. And so the step above that backtest is what we call a benchmark. And here, what we have is on the vertical axis, now we're talking about tables. So these are a bunch of different representative tables across different industries, different types of data. And then on the x-axis is, again, time. And we're strictly running the algorithm, again, on each of these tables iteratively through time, and identifying, is it firing an anomaly or not? Is it a near miss or not? This becomes the control set, right? So we can use this to have a baseline understanding of how likely is this algorithm to alert on data that hasn't been messed up. Then we go in and introduce chaos. And so we have a random chaos generator that will randomly select types of chaos, randomly select fractions of chaos to apply, randomly select columns to apply it to, and then keep trying until it gets a chaos that can take. Because sometimes you can't introduce chaos. For example, maybe the column's already 100% null. So adding more null values wouldn't be a sensible chaos operation. And then we can again rerun the algorithm on that data that has chaos introduced. And ask the question, how often is it firing anomalies? And on the basis of this, you can do sensitivity and specificity. You can do AUC. You can slice and dice this to understand what types of chaos is the algorithm able to detect, how much time does it need to be able to detect the chaos. And it becomes a pretty robust way to be able to kind of benchmark and control this. So that's it. That's how it works, what's happening behind the scenes at a high level. If you'd like to try it, I would encourage you to try it out on Databricks. We're actually a part of the Partner Connect ecosystem. So in your Databricks console, you can go into Partner Connect, and you can see Anomalo there under data quality. You'll just need to click into that and then create your account. Just put in your name, and it'll automatically spin up resources to do the querying for you in your Databricks cluster, and you can set up and configure 5 tables to begin running this and see what it looks like for yourself. So that's it. Thank you so much. Happy to take some questions, and happy to stick around a little bit after to take others.
Only question I had was about the random distribution that you allow Databricks to pull back.
Yes.
What if you have some subject matter expertise around your own specific data where you need to define the distribution approach?
Yeah, so there's a couple of different ways to do that. One we often see is to create views. So you can just easily create a view, and then you can completely control whatever you want to present to the algorithm, and then run Anomalo on that. So that's one common approach. We also have other variants of this. So there's a fun variant where you want to compare 2 SQL queries using this algorithm. And then literally you just in the UI, when you're creating a check, you just drop in the SQL that you want to compare, and it'll run the same algorithm on those 2 static SQL queries.
And the other thing is, in terms of use cases, what have you seen it be very successful in? No, actually, scratch that. What is it least successful in your opinion?
Well, so I think it goes back to comparing to validation rules and metrics. And the limitations that I described there. So if you're looking to find a needle in the haystack, right, you want to find a change in a column that's only affecting 0.1% of the data, that's almost impossible to do. It's impossible to do because this algorithm would, if it was sensitive enough to find changes like that, it would find so many of those changes that you wouldn't find it to be useful. And so ultimately, you need to be able to either create something like a view to say, I actually really want to pay attention to the clicks in this ad stream data, or you should set up a metric for the statistic or set up a validation rule to capture the explicit intent. This is really just looking for macro changes happening in the data. Other questions?
So you mentioned clusters of columns. I got the sense that was like these columns form the same bad res. wasn't sure. I want to know, what about like if this combination of columns, this combination of values produces the bad row? So it isn't just this one column, it's several of them. How well do you perform with that?
Yeah, actually really, really well. So in the way the algorithm works, it's not actually looking at column by column. It's looking at the table as a whole, right? The machine learning algorithm has access to the entire context for every row. And so one of my favorite examples is take that price per ticket column and shuffle it. Don't actually change any of its values. Leave all the values the same, but just randomly resort them. And so you actually haven't changed the mean or any statistic computed on the price per ticket, but what you have changed is the relationship between price per ticket and all of the other columns. And the algorithm is able to very clearly identify that the relationship between price per ticket and total price is broken, between price per ticket and number of tickets, between price per ticket and list ID and type of event, and summarize those issues. So it's able to find those very accurately.
I think we're out of time, but Jeremy, I hear that you're a really good technical author. Is there a blog that people can check out to go read?
Yeah, absolutely. If you go to anomalo.com, that's our website. We have a blog. I've actually written a post specific to this topic on unsupervised data monitoring. We also have, it's in kind of the ideas section of our blog. We have a bunch of other blogs that talk about things like metrics monitoring, about validation rules, about the root cause analysis that I went through. So a lot of great content in there. So thank you for pointing that out.
No problem. And one last question, any upcoming events besides this one?
Oh, that's a great question. Yeah, so we absolutely will be doing more events. I'm not 100% sure which ones we're going to be in. I know there's a few Chief Data Analytics Officer events that we'll be going to in Boston and Texas. And I'm sure there'll be others as conference season continues to evolve.
Awesome. Thank you so much, Jeremy. I apologize, we're out of time. I'm getting yelled at. But if you have more questions, come see Jeremy. Go check out his awesome blog. Go check out Anomalo inside of the new Databricks Partner Connect. Yeah. Thank you all for joining the very last session. Yep.
Thank you, everyone.
Cheers.